So at this point, our second cameo, our first cameo ends, and the second one starts. So now I want to talk about angular momentum and spin. These things are sometimes loosely called spin. We'll see at the end, spin has a very particular meaning in quantum mechanics for small objects. And loosely speaking, if we have a spinning object, then it has angular momentum. And the way to know where it points, well, the rule is, and you'll see more of this in a moment, that you curl your fingers of your right hand in the direction of the spin or the motion, and your right thumb tells you which direction the angular momentum points. So here's something, and I spin it up. Which way is the angular momentum pointing? Up. Everybody's mentally at least done this. Fingers in the direction of the motion, curling around, then one's right thumb points up. So that is the direction of the angular motion. If you think about it, a vector this way is the only unique thing about something taking place in a plane. And so that's a very natural definition that we have for the angular momentum. So if we're going to discuss momentum, think of linear momentum. For a moment, we have a mass and a velocity. In the angular momentum, we have an angular mass and an angular velocity. And so here we take an example of a dumbbell of two masses separated by a distance 2x. So each of these masses, m, is a distance x away from this axis. And if it's rotating around in the direction that I've indicated with the green arrow, then we've got some angular motion in this direction. And that's called the angular velocity. And there's an angular mass associated with these masses off the axis doing the rotation. And the angular momentum is the angular mass times the angular velocity. So think of P is equal to mv. Here we have L is equal to I omega. So L is parallel to omega, at least in simple cases. Unless you have a very odd-shaped body, then the angular momentum and the rotational direction are parallel to each other. So let us see some more about angular mass. If we have the angular momentum L, it's going to point along this direction of rotation, and the masses are moving a distance x away from the axis, and the angular mass, called the moment of inertia, is the mass times the square of the distance from the axis that they are. And I've put a 2 here simply because there are 2 of them participating. But in general terms, it's just the mass times the square of the distance from the axis. And this is a vector, the displacement from the axis to the point of center of mass of m, and this is a vector which is its velocity. And this is the first time where we see the right-hand rule for taking a cross product. Because the angular momentum is the distance or displacement vector crossed with the momentum vector. So I'd like you to try and confirm when you look at this diagram that the angular momentum is indeed in the direction we've pretended. So you take the fingers of your right hand and you point them along the vector x. For me, it looks like this. I curl them round in the direction of v, and your thumb is in the direction of omega. So we have a vector cross product, of which much more later, and the result is a vector. There turns out to be 3 ways you can multiply vectors together. This is the second way, and the first way you may have met already being the dot product, where the answer is a number rather than a vector. Where does the vector omega cross x point? Yes? The direction of v, exactly. So if we take omega, I think I have to turn around to do this one. Omega, I rotate my fingers towards in the direction of x, and v is in the direction of my outstretched right thumb. So this is a really, really great engine. If I know where the angular velocity of an object is pointing, I can say at any point where the bits of the object or the particle are moving. So if, for instance, I ask, where's this thing moving? If we have a rotation like this, you could work that out by taking omega and crossing it with the x, which takes you to that other mass. So omega cross x that way, and that mass at the top is moving in this direction. Right. So let us look at Newton's laws for angular motion. We have the angular momentum, L is equal to I omega, and Newton's first law says if there's no torque, that is the angular equivalent of force, which we'll come to, then angular momentum is conserved. The magnitude and the direction of the angular momentum doesn't change. So what else is angular momentum? So there's the Earth and the Moon. The Moon is going around the Earth is spinning on its own axis, and they together have angular momentum, and that angular momentum is conserved. Whatever's happening with the tides and friction and so on, the angular momentum is constant. And here's the bicycle wheel. Which way is it turning? It's turning anti-clockwise, absolutely. Well done. So protons, electrons, nuclei, neutrinos, they're all quantum objects, and those particular ones, they all have spin. And here's a spaceman in the space lab, and he's got a spinning wheel here, do you see? And he's talking to the audience. He's keeping it in the picture by hitting it. And right now, he's going to tell you which way it's spinning. So it's a universal convention, you see. He's in space. He's still doing this with his right hand. Now, the next question you can ask is, if we have Newton's first law, which says that angular momentum doesn't change if you don't have an external torque, then can the motion change its character in time? Or is it like a tennis ball traveling forever, rather boring? And the answer in the angular case is interesting things can happen. And the reason for that is that unlike ordinary mass, you can change your angular mass quite effectively. And if you change your angular mass, then at constant angular momentum, the motion can become more interesting. So there's an example of an ice skater. The ice skater will have a constant angular momentum. You'll be able to work out which direction it's pointing. And he changes his angular mass and has to change his angular motion in order that his angular momentum is unchanged. And here we have an example of that. Spinning. Now he pulls his legs and arms in and spins a lot faster. And then through friction, his angular motion comes to an end. So I would like to demonstrate that. And for this demonstration, it would be useful to have somebody who would like to sit on this seat while I spin them up. Do we have a volunteer? Not many. Would you? Right, if you'd like to climb out and... If you'd like to sit on that seat and sit comfortably so that your legs are no longer touching the floor. That leg's still touching the floor, so...
So I don't spin round.
Right, okay. So if you take these and hold them at arm's length, yep, you won't hit the blackboard because we've tested that. Now I will spin you up a little bit, and now pull these into the center of your chest. Right in. And out again. And in again, right into the center of your chest. You see a very noticeable change in speed. Where is his angular momentum pointing? Down, through the floor. Okay, that's very good. Now, can you get off without falling over? You're not dizzy?
No.
Very good. I have seen people fall over after that experience. So his angular momentum was down and it was unchanging, but his angular mass was changing. And because it goes as the square of the distance, it's a nice long way out. The masses were reasonable, but not high compared with his own mass. But pulling them in made a huge difference to 2mx squared. X squared went from a meter to nothing. So that's a good example of changing your angular motion without changing your angular momentum. Here's another example. There's a cat. The cat has 0 angular momentum, and it is then dropped. And it's dropped from the top of the wall here, upside down, down the wall. Now the cat at this point sets his tail into motion around his axle like this. And if his angular momentum is constant, then his body has to rotate in the opposite direction. And it rotates long enough that by the time he lands on the ground and stops his tail rotating, his body stops rotating and the feet are pointing at the ground. So he's gone through pi radians in this short fall from the top to the bottom of the wall. So this is, I think, a Victorian example of a cat righting itself in mid-air. So we can emulate that a bit by trying to analyze this situation. Here we have somebody sitting on a seat, and this person will sit on a seat as I am now, and we'll have a wheel. I'll take this wheel for the time being. And the wheel is spinning, and guess it's spinning this way. And the total angular momentum is simply that of the spinning wheel. Then what happens if you turn this wheel over while it's spinning? Let's look at that carefully. The wheel is now pointing down, and its angular momentum, which I've put in green here, is pointing down because we've turned the wheel over. The total angular momentum is still this blue value, which is the same in magnitude as this value. And if the total is to remain this blue one, we've turned the green one over, then we have to have twice as much angular momentum of the person sitting on the seat. So we could try that one as well, and this is where I would call upon another volunteer. Do we have another volunteer? If not, I will ask Dr. Conterio to come up forward. Do we have one? Yes, okay. Can you come forward? However, this time I don't have such an innocent wheel. I've got this one, for which I need leather gloves. Would you like to sit down on the seat and sit far enough back that your feet are off the ground and that you are comfortable? And you will have to hold this wheel so that its axle is vertical in front of you, far enough from your body that the wheel doesn't strike you as it rotates. So here we go. Now this wheel may be rotating too quickly, so I'll try and hold you if necessary. Now if you can rotate the wheel so it points the other way up. And I think this is going to be too dangerous. So if you would like to, no, just stay there, and I will slow this wheel down so that the effect is not nearly so pronounced. Hold it vertical if you can. Now, nice and vertical, that's it. And you'll notice he's facing you. This will be important later. Now turn the wheel over till it's pointing vertically. Can you keep rotating this further up so it's vertical? It's getting a bit quick, isn't it? And rotate it the other way, back to where you started. So, very good. So he can change his angular motion by turning this wheel over. So let me take this from you, and I'll try this again myself. Thank you. Very good. So, these are quite heavy. There's lead weight, a strip of lead underneath the silvery tape. So I'm going to try this again. I rotate this around, and I'm spinning like this, and then I can stop in any direction I like. Now, I'm on an almost frictionless seat, and it would be impossible to turn to face the other way by simply jiggling around, as you can see. But if I do this, then I've got perfect control about where I point. Now, you might say that this is a bit academic, but this is how spacecraft change their orientation. There's nothing to hook onto in space, and therefore you have to have some way of changing your angular motion, and then when you're ready, unchanging it. So it's a perfect way of reorienting yourself in space. And you're not changing your angular momentum. The angular momentum is 0. What you're doing is reattributing the various parts. But this is a very smooth seat, and you can see that only by a very small friction can I gradually turn round. And that is the problem that is solved by this sort of angular momentum conservation. So motion and orientation change when you change your constituent parts, if you like. So this is the demonstration of reorientation in outer space. So far, we've been talking about examples of angular momentum which is unchanged because there's no external torques or angular forces acting on the system. Now let's look at the case where we change the angular momentum.